The pre-stack inversion is an exciting tool when it comes to Kingdom because now we're able to differentiate between our fluids and our rocks, but also we can differentiate between the fluids themselves. So we're able to tell the difference between our gas sands, our oil sands, and our wet sands. And what I'll do is start loading the data and show you how we can do this now. So here I'm selecting my sonic log. This is my shear sonic. This is the density log and the time depth curve. So once these are loaded, as we've seen in the other two inversion packages, we have our calibrated log on the plot here. Now we have all of these different logs, so very quickly our VP, our VS, our density, acoustic impedance, shear impedance, gradient impedance, VP over VS, and Poisson's ratio. Now the VP over VS is useful for discriminating between fluid and lithology in a conventional reservoir. And in the unconventional shale gas, you might use something like Young's modulus over Poisson's ratio, for example. So we can show this here. And we've got Lambda-Rho and Mu-Rho useful for both types of reservoirs. Now there's different log display options, and we can change the units here. So if we want to swap between the display units or the velocity units, we can change these, for example, between feet and meters per second. Now we have the despike tool option as well, but we're just going to kind of skip through that because our logs are looking fairly well conditioned in this project. Here, just to describe it, we have the chi value up here, and the EEI, which is extended elastic impedance, and the GI, which is the gradient impedance, require this chi angle and the K value for us to use in subsequent parts of the software. So just keep an eye out for those. And the K value is the average of VS over VP squared. And this is from the log or input, but we'll come back to that later. On this plot, you can also display a number of different, for example, porosity. We can display those logs as well. But let's get on to the exciting part, which is the cross plot. Now, this is where the software gets really cool. The theory behind this is that the physical space that the different properties lie on the cross plot relate to whether they are a gas-charged sand, an oil-filled sand, or a brine-filled sand, and the direction that they move in relate to these different properties. So we'll have, for example, on a mu by Lambda-Rho plot, the increasing probability of sand in this direction, and our different zones might separate like so. Now in the software, on the crossplot tab here, first of all we're going to change the plot option to AI, which is our acoustic impedance, versus our VP VS, like so. And we can see that we have our separation of our gas sands, our oil sands, and our brine sands from the background material. Now, if I change the color on this log to clay, which is also our V-shale, what we see here is the lithology being discriminated again, with this showing the sand versus the shale. If we now change this to porosity, which is phi, what we're now looking at is that with higher porosity values, we're seeing our sands, and our lower porosity is showing our background lithology, and this is going to discriminate our reservoir quality. If we now change this to the saturation of water, SW, what we now see is that we have our oil and our gas sands standing out. So this is showing the hydrocarbons from the brine. And now, if we change this from SW to SG, we're now showing the gas sand and separating our gas from our other data values. If we have a look at this in the Lambda-Rho mu or LMR space, plotted by our saturation of gas, what you can see here is that the same data is stretched and rotated in different ways. The key thing is that there is an assumption that a calibration has been performed in the LMR space. And we can see that these plots plot like so. If we have a look at the Young's modulus versus Poisson's ratio, well, in the unconventionals, if we have a look here at the porosity, then we can see that lower Young's modulus is happening at higher porosities, where we have stiffer rocks and shales. In the unconventional space, these might be described as compliant and non-compliant rocks. If we have a look at the AI versus VP/VS and change this to our Young's modulus, we can see how this is sensitive to fluids. If we have a look in this space and colour it by the saturation of gas, for example, we might want to have a look at the domain. So here we're in the depth domain and we have lots of data points working in the centimeters resolution. If I select the time domain, we can see that we have radically fewer data points as we change our resolution from 25 centimeters to in the region of 10 to 40 meters. Now this enables to see if we get separation of our data points with decreasing quality seismic. So here, if, for example, we select 20 Hertz, you see that it's less easy to separate and discriminate between these. Now this is a synthetic data set, again, so these are visible here, but it may be that on a real project that you wouldn't be able to see them. Here, if we change to 40, we get some separation, but they're not necessarily fully separated. Here, if we get up to 80, we can see that they plot back in this space, showing good separation. Now, this is our feasibility, and this is one of the main things that enables us to discern between the difference between gas and water. Now, one of the key things here, if I just swap this back to the depth domain, is okay, we've separated these and we've determined that this is our gas area. Where might this be? We can draw a polygon around these points, like so. And now if we look on the log analysis plot, this is our gas sand. And that's pretty cool, and that's where the inversion really becomes a very powerful tool when you have access to these attributes. Now, in performing this, one of the key questions is, does this all make geological sense? Do the IP, or AI, wavelet, and seismic all seem to be consistent? Does the same thing happen for P, S, and density? Well, then we want to start looking at, do we have enough information for a background model? If not, we may want to look at an AI over GI, as it's not so dependent on the background model. Is there too much noise on the far angles? If you have, you've got less ability to discriminate between fluids and geomechanical properties. If wells don't match the seismic, the inversion won't work, so maybe you'd need to reprocess that, or look at the petrophysics, the log quality, etc. One of the great things about Kingdom is we have all of this in one system, and where necessary, it may be that you can go back in Kingdom and work over it where required. Next, you might want to be asking yourself, what are the potential false negatives or false positives? And can you solve these in different scales, be they meters or milliseconds? And what is the relative weighting between the background model and the band-limited inversion or relative inversion? This tool is going to work for a range of data quality and ranges of different quality well ties. So one of the key things is that we've got all of these plots possible and appropriate to interact with as you step through this whole QC process. The extended elastic impedance is a function of this chi angle, and we can scan chi for every degree and compare the EEI with any target log, like so. Now for our gradient impedance, we have a maximum positive correlation of almost 1 and a chi-angle of 90 degrees. For our acoustic impedance, we have the same positive correlation, but with an optimal chi-angle of 0. Now, whether the angle is positive or negative, you can see here in this space, so VPVS, Poisson's ratio, Lambda-Rho, all having positive correlations. But if, for example, we look at our phi, our porosity, we can see that we don't get a match here, and we have a negative correlation. If we swap into the negative space like so, we can see that we have a reverse phase, and now we have a much better match. So from here, I think it's important to address kind of what does this chi-angle mean? Well, if we have a look at this cross plot and we change to, for example, AI versus GI, and we have a look at the porosity, and we swap to the depth domain, if you imagine that all of these data values were rotated anti-clockwise, so a negative 16 degrees, we'd get something like this. And we can see that the low and high porosity values would tend to line up over the same x-axes. After rotation, if we collapsed all values on the x-axis, this would be equivalent to the porosity prediction from EEI. And you might notice that even after rotation, there is some overlap for low porosity sand and shale data, which are highlighted here in the blue and green areas, with the fluid and lithology effects having an impact on the accuracy of the porosity prediction. Now the last thing to note is that if we want to generate the porosity of the reservoir, we can set up the time depth window, and then we can note the optimum chi-angle for each of the 5 parameters chosen. So for example, our TOC, our V-shale, our AI, our water saturation, and our porosity. Once we'd have all of those listed, we can take the values from down here, then we'll move forward to our pre-stack data analysis. On the pre-stack data analysis tab, this is where we'll do our AVO analysis of our pre-stack data. And what we'll start off with is having a look at our A and B stacks, and we'll change here to the EEI, and this value in degrees is pulled from the previous page. Now when we select this, we can see that the volume that we're going to create is the EEI reflectivity volume, and what it requires is our normal incidence A and our gradient stacks B, and these are stored in Kingdom. What we would do is, we don't have them in this project, but let's just say that this one was called A. We would select that for A. We'd select the other option for B, and then down here we have our time window of say 1 to 2 seconds, so we can target this process for improved speed, and we would hit start, and this would take about 5 minutes to generate. So this would be our EEI reflectivity volume that we'd create with the name like so. If we look at the Cascaded Pre-stack Inversion option here, we also have our A and B stacks, and the volume that we're going to generate here is the S reflectivity volume. Now you can note here that the A stack is our P wave equivalent, where our P wave reflectivity is at 0 offset. But it's actually the S stack that is required here to do the pre-stack inversion. So once we'd chosen those values with the CPI and set our target window and click start, these would take about 20 minutes to run for this. Now, if we have a look at our angle stacks with this option, and we see the CPI is selected, here you can see that we have the P reflectivity and S reflectivity that we're going to generate. And what you'll see from the list of options is that we can work with our two-term AVO. Now for this project we're going to select 6, like so. I'll just click these buttons up to 6, and from here we're then going to select our angle stack 1 and select our 5, angle stack 2, 10, and change this value to 10 as well, angle stack 3, 15, change this to 15, angle stack 4, 20, angle stack 5, 25, and angle stack 6, 30. So now that they are all input and we see that those files are corresponding, then we have a number of different things that we can do. So we can process this using a constant Vs over Vp value, and this can be calculated from the real log values. We can define some vertical extent in the Vs and Vp logs so that there is some variation with time. So if we select this option, if we remember on our log analysis plot, these would be our Vp and Vs logs that we would derive this information from. If, for example, we were looking at the Vp volume, then the Vp volume comes from these Vs and Vp values, which are our gamma and delta values, and you can see that these have been auto-populated here, like so. Now if we have a look on our cross plot and we have a look at our Vp versus Vs, we can see that we have these gamma and delta values populated up here, and we can look at these in the linear scale and the log scale, like so. So these values will come in and will populate here. Now we can use these values with the Vp volume if we're not happy with a constant or a log. And in using these gamma and delta values from the cross plot, this will generate the Vp over Vs for the entire volume. Okay, so once those are selected and parameterized, again these will output our P and S, and click start, and away we go. In here we also have the option for our Vs and Vp volumes, and this option is to select a pre-existing volume for use. Now this would come from a processing shop, for example, and here we have the Vp and Vs options that we would choose from this drop-down list. Again, we don't have them in this synthetic project, but these would be maybe more rare to have, but if you have them you could select these and you could process it using those values like so. So all fairly straightforward. You're just selecting the different options, selecting the relevant file, clicking start and letting it process. Now here we can see, if we come back to, for example, the constant, that when we've been working with our value so far, we've got the 2-term AVO, and this comes from the author Fatty and his equation, where we can derive the P reflectivity and the S reflectivity from our angle stacks, or from our offset stacks where the angles are shorter. Now these will just derive the 2 terms P and S. If we go to the 3-term AVO, what we are going to do here is use the regress of the Fatty equation and use that again, but the 3rd term is the density, and this is rho, and we now see that we have our 3 volumes, P, S and density, that we can create like so. Now one of the key things to note here is that when we go to our 3-term AVO, the number of angles that we need needs to be larger than our 2-term AVO, and these reflectivity volumes require these very long offsets which are required in the acquisition. So in order to do this, we're going to select up to 9, and we have our 1, 2, 3, 4, 5, 6 and our values in degrees selected. Here we're going to choose our AS7, So this will be 35, and enter in 35 here. AS8 is 40, enter 40 here, and AS9 is 45. Enter that there. Now the key thing to note is that if you have less than 40 degrees in these longer offsets, then the software will give you a warning that the offset is too short and you cannot proceed. So this is very data specific. With our angle sacks chosen for these values, we need to understand that all of the data wants to be fully QC'd and conditioned in Kingdom before proceeding with this process, because the whole idea here is that we're going to effectively work with all of these gathers, effectively with 9 like this. It's a super gather, and we're going to generate these 3 volumes. Now if you have garbage going in, you're going to get garbage coming out. So it's really important that all of these options that you're selecting are really well conditioned in Kingdom. So that's a step that we're not going to discuss here, but that needs to happen. You can see that this least square damping is on, and this default value is typically okay. And when you click start, it's going to take about 20 minutes to run for each of these 3 volumes. If, for example, you had a very large project with, say, 1 million traces, that runtime would be about 2 hours per volume. So not necessarily so long to get all of these 3 volumes out. The key thing now is that you must close and reopen Kingdom. So if we assume that we've just done that as part of this demo, what we're now going to do is go on to the next part, which is going to be our acoustic impedance. So we'll pretend that we've closed Kingdom and reopen it again, and we're ready for the next section. For the acoustic impedance, we'll open our data like so. So we'll do the DT, the density, the time depth chart, and here we're going to select the 2D grid and the amplitudes. Now here we're going to select the RP 2T AVO at 80 Hz, and in comparison here the higher frequency is going to provide better discrimination capability for us. And now we're on the log size match screen. Now because this is a 2D data set and we're just working with one line, I'm now just going to load this PowerPoint slide and show you what this might look like on a 3D project. Here we can see the impedance log. Here we have the seismic itself, and we have these red lines which describe our start time and end time for our window. This is a bird's eye view looking down at our well on this black dot here. This trace here is the closest trace to our well, and all of the boxes with all of the different colours relate to our seismic traces around our well. Now what we're looking at here are the predictability values for the log size match process that the SA inversion optimization is going to use for the matching process. What this is saying to us is that this trace here is the optimal trace to do this matching trace on, and if we imagine the traces here are 12.5 meter bin spacing, we're about 100 meters away from the well. So quite close, and we are going to select this trace automatically. Now here we have our window start and end time, we have our inlines and crosslines set. Again, it's a 2D line. We also have the bandwidth ratio that we could look at and the time shift. Again, these are extra QCs, but on this 2D data set we don't have those available. So I'm going to press next. What we come to now is the Wavelets and Spectra tab, and what we see here is we have our window start time and end time for our log, so we can zoom in here for example. We have our log reflectivity coefficient, the seismic, the synthetic, and the error trace. Now the key component for this to process is that our correlation coefficient must be over 0.7. So here we have this very high value. Let's say that we wanted to have a look at the wavelets and spectra. Here you can see the wavelet and the amplitude and phase spectrums respectively, and you might want to do some smoothing. So let's say for example we want to increase the smoothing here up to 25. So that will just adjust like so. What we're able to do if you didn't have this would be to select the import wavelet, where we can import from the Kingdom Suite, from ASCII pairs, from Hampson-Russell, or from seg-y, and you'd select import from file and load the relevant wavelets in, and hopefully improve your correlation coefficient. One of the key features of the software is that we can also work with average wavelets. So in the project here, we'll just use these wavelets that we've prepared, like so. Select this, and I'm going to add these 4 wavelets so you can see how the software can add these together like so. So number 3, and last but not least, number 4. So on here we now have these 4 wavelets selected. We can see their legend here shows the different color, and as you select these you'll see that the color comes to top for the relevant wavelet. So if we wanted to use these for a project, we'd select use average wavelet for the SA inversion, and we would proceed. So now we've done this and we're happy with our wavelet and the corresponding correlation coefficient, we're going to press next. So on the next screen here we have the scalar that's going to be applied, and this is calculated automatically for us owing to the values that we set for our time window. You can see up here that it says macro model select. So on here we have the macro model drop down, and in this instance we're just going to select acoustic impedance log. So this will enable us to process more quickly. So here the software is now taking us to the last of these 4 screens, which is the SA inversion screen, and you can see our acoustic impedance units are on the x-axis here. Here I'm going to select the inversion calculation parameters tab, and because we've used this log, we can change the smoothing here. So for example, we can change this to 8, and if we click apply, we can see how the cyan color macro model changes on this plot. We have the red as the impedance log, the black as the inverted impedance, and these are the bounds. So here we're able to use this as a quick pass for us to proceed. However, it can be noted that we might want to use the high def to actually build a 3D macro model, and to be able to have the very detailed velocity model applied to the whole volume. Now that's something that we'll come back to at the end. If we look here, what we can see in this section is the maximum correlation, and this effectively is saying that we have 82%, so it's quite a good one to go on with. Obviously as we go toward 1, that would be the best. And this enables us to see the quality that we should be expecting from the output. Now when we have a look up here at the macro model conversion, we can see that we've got the alpha, beta, delta and gamma values, and these are the selection that comes from the crossplot equations that we covered earlier. Soon these will be automated to be retrieved from those plots, but you can manually adjust them if you want to. From here, once we're happy with these various parameters, because we can change the various parameters up here to increase the performance of our SA inversion, we'll assume that we've done all of that, and then we'll press apply to volume. Now here we can see that we have our volume in as our RP 2T AVO, and then we're going to have our volumes out as our absolute, relative and synthetic volumes. And if we select the synthetic here, it's just important to note that this will also increase the hard disk space. Now this is a targeted processing operation, and rather than run the inversion on the whole volume and take a lot of processing time, we're going to focus on the areas of interest. So here we have the trace start time and end time. We can enter a constant time as a start time and end time, or we can follow a grid with a plus and minus deviation. So here, if I just close this up, if we had our grids listed, we could select our top grid and our bottom grid, and for example, we could follow those grids with, say, a plus 50 or a minus 50 deviation. So nice and easy to set up and parameterize. One of the key things to note here is the number of cores on my computer. So I here have 8 processing cores. The more cores you have, the better. So let's say that this would take 8 hours to overnight to run. If we up this to 24 cores, it's going to run 3 times more quickly. Once this has been parameterized and set, you press invert, and then this is going to set the volume running. So on a medium-sized project, it's going to take perhaps, say, overnight. As your project size increases, you're going to take longer and longer. But we should be talking in, no more than, a couple of days, for example, for it to run, even on a large project size. Once that's processed, we'll assume that that's all good, and now we'll move forward to the next section, which is the shear impedance. With the shear impedance now, I will move through this more quickly. So here we're going to select the dt, the SDT, the density, and the depth time curve. And when we click on the survey here, the key thing to note is that we're now going to use the S reflectivity volume that we created earlier, which is the RS2T AVO 80 Hz. Now, if we think about this in terms of the processing time, this was created yesterday. And for the purpose of our demonstration, we've obviously got it all ready to go. Now, the next thing that we have to do is select our macro model. And here, what we're able to do is select this SI model as our macro model. And we can see that we have 4 options come up, and we're going to select the shear impedance volume. Now, you can note that this is perhaps rare, and it's the best one to use. If you don't have this, you can use the P-way velocity volume in this instance. But we're going to use the shear impedance, so we'll select that. Now, the next thing that we are going to do is we have our AI model, so we could go and select here. But just to show you, we also have the ability to select our AI model from here. And in this instance, we are going to use the acoustic impedance log. Now, this is a really, really important point that we need to make. And that here we're constraining the inversion by this AI model. And this is a constraint for both the P and the S models. And what we're doing is understanding the VP over VS ratio as we're doing the inversion and using this as the constraint. So when we're chatting to the customers and we are understanding their requirements, they might ask us questions such as how are we maintaining the relationship between VP over VS, how are you constraining your shear, how are you ensuring the physics is consistent between my well and the VPVS or P or S and the inversion results. And it's very important here that we stress that this inversion is unique. It's being constrained by the AI model. It's not an independent inversion, and it's this AI which is the constraint. Now, for example, if you want to do a quick and dirty job here, under this macro model, you could select the shear impedance log rather than the volume, and we could run that in that instance. But because we have this shear impedance volume, we're going to select this and we're going to move forward. So very quickly, for the wavelet estimation, we will click next. For the seismic scalar estimation, again, we could go through this, but I'm going to click next. And what we'll see here is that it takes a bit longer to load than the AI, as it has to invert the traces which are being constrained by the AI model. So again, another important point to note. Now for the SA inversion, we can now see on the x-axis that we have the shear impedance. And what we're able to do in the inversion calculation parameters tab is QC the quality of the inversion in this this tab. We also have the seismic section view where we can have a look here at that for the QC purposes, and we also have the SA algorithm which shows how the software is coming to its deterministic answer. So from here we've got these, for example, weights for the VSVP. This is 1, this is suitable, and I'm going to click on apply to volume. The key thing here is that we have our input as our RS, we have our outputs as our absolute, relative and synthetic, and we have the tick box again, and we can click invert. Just make sure whether you want this, as it can be heavy on HDD space, and on once we've done this, let's move on to the next part, as we've just done the second stage of our 3-part process, and now we'll go on to density. So click OK. On the density option, we can select the DT and density and our time depth curve. And now when we're making our selection with our amplitudes, here we're going to select our RD 3-term AVO, with the density being the 3rd term. Now it's really important here to note that this is only possible with long offset data, but the long offset data is often quite noisy. So it's not just having the angles themselves that enable us to do this, but having good quality information at the zone of interest. And it's very important that you ensure that you have consistent information there that's not too noisy. Now in Kingdom, straddle slicing is good for QCing this far angle data, and this is what we'd need to do before we would have created this reflectivity density volume, like so. Now here we'll just use the macro model, drop down and choose the density log. Then in the AI model we'll use this drop down and use the acoustic impedance log as the AI constraint. And it's important to note that it's the density component here which is used to constrain the density inversion, whereas the high frequency component comes from the seismic. At this stage, we want to have looked at the petrophysics and the mudrock line and ensure that these parameters are reasonable before we would proceed. So in here, we'll press next. And once this moves forward, again, we might select our appropriate time windows and so forth. This will take us on now to the SA inversion page, where again we see density on the x-axis. So here in the inversion calculation parameters tab, we are having a look at these relative values. We can see the max correlation in this, which gives us an understanding of the quality of the inversion. Here we see the weight for density being 1. Again, this is usually suitable, and we can turn this on and off to see how the constraint with the AI model is working for us positively or not when this goes to 0. Now again, what we'll do is we'll click on apply to volume. Again, we've got our selection here as our inputs. We have our outputs, absolute, relative and synthetic, with their names. We have the targeted processing for us to speed up. We've got the multiple cores. Again, all of this just going through. Click on invert and that will then process. So just a final point here, that the shear volume is going to take 8 hours to overnight. The density volume is going to take 8 hours to overnight. So we've just done, inverted commas, 2 days worth of processing time. And now we'll move on to the next part of the process, which is coming back into the pre-stack inversion. And we have everything now ready for our elastic parameter transforms. For this section, we will open up our well again, select our DT, our SDT, our density, and our time depth curve. And this is important to do to ensure that the well is calibrated before we proceed. So on here with our Elastic Parameter Transforms tab, we have our 3 tabs here of Acoustic Impedance, Shear Impedance, and Density. And you can note that all of the amplitudes are going to be greater than 0, as we're now dealing with our absolute values and not our relative ones. So for our inputs, we're now going to select these volumes. So this is going to be our AI absolute, 2T at 80 Hz. For the shear impedance, this will be our SI absolute, 2T at 80 Hz. And for our density, this is going to be our Rho absolute, 3T at 80 Hz. So once these inputs are selected, we're in a situation whereby we now can generate our volumes that we want to transform. And it's important to keep in mind what the purpose of the project is and what the most suitable volumes are for that. So for this, for example, let's say that you wanted to work on a conventional reservoir. The VP-VS ratio with, for example, the relative impedance volume would be used because it'd be easier to interpret as the background model has been removed. This would be done so that you'd select your time window and you'd click transform and away the software goes. Now it'll take about 30 minutes for each of these 3 volumes to generate, so that would be an hour and a half in total. And if you select the relative options, then it will double that. So there would be 6 volumes and we would have double the hard disk space. Now for our shale reservoir, we're going to be maybe more interested in the Poisson's ratio, the Young's modulus, and the Young's modulus over Poisson's ratio. And these again, we can select these values, select the time, and click transform. Now, when we're thinking about these volumes overall, these top 5 volumes, so the VPVS, Poisson's ratio, Lambda-Rho, Mu-Rho, and Lambda-Mu, none of these require density. So we're able to use these whether we have a 2-term or a 3-term option. But without the density, these don't matter. If we look at these parameters here, the Young's modulus over Poisson's ratio, the gradient impedance, and the extended elastic impedance, these 4 do require density. Now, one key thing to note is that within Kingdom Seismic Inversion, we do have an algorithm that can approximate density using our GI and EEI and basically back calculate the density for these other options. So if you are stuck, then there is a way around it that we can use for this. Now, if we remember back to our EEI correlation, on here we have the petrophysical parameters that we wanted to identify. And if, for example, we select the chi-angles here to be 5, then we have the option to select our chi-angle for our porosity, our gamma ray, our water saturation, our V-shale, and our total organic carbon, our TOC. And what we'd be able to do in this instance is enter those values, again select the time window and click transform. Now, it's just quite important to reiterate that if you're looking at how much hard disk space you're going to take up with these processes, then this would generate 5 volumes, this would be 10, 15, 20, and so on. So you want to be really careful with which of these tick boxes are selected and not selected before you click this transform button, as you'll take half an hour per volume, but also be having an exponential increase on the hard drive space. So with all of that noted and with those volumes created, what we'll now do is move on to our litho fluid mapping. Now, on our litho fluid mapping tab, what we have to do first of all is select our volume in. So on here, we're going to select our AI absolute and select our acoustic impedance. And we can then plot that on the y-axis of the graph here that we're going to make against, for example, our VP over VS. So here we'll select this and we have our values like so. On here, if you select the porosity, our phi, we see the data points color accordingly. Now we're working on the 2D synthetic data set, so we only have one inline and one crossline. But if you're working with 3D data, you'd be able to select this to a 5x5 grid, for example, and see the impact on the data points. Now the purpose of this plot is that we can use this to start identifying our fluids from our background rocks. And if we remember back to our separation plots, here we can start drawing some polygons. So on here, let me select these 4 dots, and these are going to be our gas sand values. So here on this option, we can see that our gas sand pops out here and is in a nice correlation with the well here. So I can select the porosity and we can see that we get a nice match on this spike. Now if we were dealing with a 3D volume, what we'd be able to do is change the amplitudes on this display. And you might think this is the seismic, but this background is of the wiggle trace is the AI impedance with the background model removed to look like the seismic. So it's a bit of a trick that we've done to give you this visualization without having to load the seismic itself. Now in terms of the projection here, what we're able to do if it was a 3D is you'd be able to move around in this space and you'd be able to move around and see where this was located in terms of these fluids or gases or so forth. If you get lost, you can click to nearest and it would snap back. Now what we're going to do is draw our second polygon around our other data points. So here if we select this like so, get all of those data points included, this now would be our oil sand. And we can see that we've got separation between these two on the display as much as we have them on the data points. Here we can draw the third polygon. So on here we can draw around these values, try and get those all selected, double click here, and these would be our wet sands that would be situated in the space like so. So all of these polygons are interlinked and mapped in 3D in different colors to help you delineate and illuminate these specific areas of interest throughout these different volumes. Now the last thing to do here is to select our output. We can write our name. We can again choose the Windows start time and end time, click on start and output this volume back into Kingdom. And this is kind of the whole purpose of the pre-stack inversion, has enabled us to separate our lithology from our fluids, but then also be able to separate our fluids between themselves. And here you can very clearly see the difference between our gas sands, our oil sands, and our wet sands. So it's a very, very powerful tool. It enables you to make very clear predictions, and up to this point you will also have used it to determine the feasibility of whether you would want to work forward or not. So we'd really like you to be able to have this tool for your use, and it would be great to get you signed up for it. But there's a couple of cool other things that I'd like to show you before I conclude the presentation. So let's move on to those now. For this last section, we're going to need a 3D data set so I can show you the high def. So I'm just going to close Kingdom Seismic Inversion. And here I have the Gallian synthetic project. So in here I will select Project, Seismic Inversion, and we'll see this project load like so. So for this stage we are going to select our well again, our DT, our Rho B time depth chart, and the amplitudes. So this is all of the usual processes that we'd need to set up our colored inversion, and we can see this on the panel here. So we can have a look at the Impedance Log Spectral Analysis tab and the Spectral Shaping of Seismic Data tab. And if we look down here, we can click on the Inversion Calculation Parameters tab, and we can see the options for the Butterworth filter that we're going to apply. So here, if we look at the seismic mean spectrum, we can take this up to 80 so that we get a better fit here. And if we look at the shaping function and the match down here, we're going to want a low cutoff of say 12, and we are going to want to smooth the data. Probably let's do a Populus bandwidth of 12 Hertz as well. So this is all we need to do for our colored inversion to be able to move on with. And if we look here at the logs and seismic, we see that this is the well, this is the inversion, and we see the max correlation here. Remember, it's a synthetic data set that we're working with, but this shows us that we have a correlation of 88%, so pretty good. But this isn't what I want to show you. What's really important here is that we have the ability to use a statistical wavelet, and that the software actually can determine the true phase of the data if it's unknown. Now, I won't go into this too much, but we have this algorithm in the software that detects the true phase of the data, and here it can determine that the true phase of the data is 3 degrees, and this would be okay to proceed with this P data if the well tie is good. And one of the nice things is that this technique is actually unique to Kingdom Seismic Inversion, so you won't see this in other packages. Now, if we want to move away from the Roy-White wavelet estimation technique used in the SA inversion, this statistical wavelet that we can make can simply be exported from the colored inversion aspect and then inputted into the SA. So here you'd take this option CI statistical wavelet, enter in here, stat, etc., click save, and then use that as your input. Now, if the well tie was not so good and you had data from the processing report, you could here, for example, select false and enter in a value. So let's just say that our value was 30 degrees. Here, this would be the value that would be generated, and again we just click export CI, and it would generate this wavelet using these details. Now, for P-wave, this is estimated automatically, but for shear and density, we don't have these logs in colored inversion. So we do have this very nice option. If we can select the S-wave reflectivity, we can come back here and we can, for example, say, okay, well, with the S-wave, we're going to need a bit of a lower cutoff, for example. And then we might say, okay, well, from the processing report, for example, let's say that the value was 67, and we could then export this. And we repeat this for density, and this is a very nice option to give us these 3 different statistical wavelets that gives us other options when we move further down the work with the pre-stack. And this is going to depend on your available data and its quality, but it's a really nice feature of the software that I just wanted to highlight before we finish. Now, lastly, the next thing to go on to is the high-def tool. So if I select Tools, SA Inversion, and Acoustic Impedance, I can get on to showing you how we can generate a high-resolution macro model in the software. In order to get this model created, we have slightly different data loading. So we're going to select the DT and then the time depth curve. And then you'll see the in high def button up here. We'll click that to say yes, and we have a high def tab go up here. And then we're going to proceed with our other wells, selecting the same option. So as we're clicking through, you can see that it's 3 clicks per well, and DT, TD, high def yes, and last but not least, just the same. Again, so once we've done this and we've selected this to yes, we're going to click on our high def tab, and we can see that we have these 4 wells calibrated here and that they are going to be used in high def. You could add other ones if you hadn't already, and you can remove them as well with these buttons. The second data type that we're going to want is our grids. So here we're going to select high def grid for upper Triassic, select for lower Triassic, for base Triassic, and when we select the base upper Permian, we want to click on Finished Apply Changes. And then the third data type that we need, if we select this, is our model for high def. And this is the Seismic Interval VP model that we are going to want to use. So if we click on yes here, then we can see that it processes in the bottom corner, and then once that has finished processing, you can see Run High Def becomes available. So let's click this and open the software. Now, this is opened on my other monitor, so it asks you, do you have a background model in a seg.y file? I'm going to click yes. It comes up with a option where we can load the model for high def.seg.y. So press open, and then do you want to add Velpac generated 2D background velocity seg.y files? We're going to click no. And once that has done, the software loads like this. Now in high def we can see a 2D map view, and we can scroll into the map to see that we have a few wells in this area. And what high def enables us to do is to take the log level detail of velocities contained within a well and propagate them through a velocity volume at that log level detail. So if we click on the profile over here, I'm just going to turn the volume type to background, and if we look at the high def tab here and we have a look at the well, we can see that the high def smoothing is through here, so the propagation will smooth through the well locations. If we turn the smooth active off, we'll see that the high def is exactly the same at the well locations, so we'll smooth the volume. Now in the profile itself, if I click this, we are going to want to probably select a line to work from. So we have a line trace range. If we just go somewhere in the middle here, click apply, and we'll see the software create this model for us. Now in working from one well, we can see the log level detail in here and our background model. It could be that we want to do, for example, a random line through our wells. So if we click 1, 2, 3, 4, 5 like this in this V shape, if we change our line type from inline to random, click apply, and now click in our profile, we can see that we've got our wells coming through like this. Now what high def does is it enables us to propagate these velocities through the volume, and it conforms to the background trend using kriging at every 2D sample interval to effectively 3D Krieg the model. So if I now select the high def option and click apply, you'll see here that we have these velocities propagating like so. Now the really cool thing is that it's very easy to use, and we can click cut from top, cut from base, for example, stretch and squeeze and background. So we click apply like so, and we can change the fill types accordingly. Now, to go into a full demonstration of high def might take 10 to 20 minutes or something like that, but just to give you an understanding that we have this very, very nice, easy to use macro model builder that's going to be the ideal input for us. And once we have worked through all of this, we're able to click on Run 3D using the batch processors, click Apply, and this would generate like so. Now, high def is absolutely critical in the pre-stack inversion, as the AI, SI, and density requires this highly detailed macro model to be used. And high def is really important for a detailed inversion with variation at each trace across the survey area. So having this macro model builder as part of Kingdom Pre-stack is really going to enable you to use the whole package. And when we talk about the whole package of tools, Kingdom is an ideal platform to perform all of this work because we have different Kingdom visualization tools, we have Kingdom petrophysics, we have AVO that we can use for the angle stacks and the intercept gradient stacks, as well as Kingdom Analytics. And this is all integrated in one easy to use package. So this concludes the presentation, and I'd love to hear your thoughts, and if you'd like to, we can get you signed up for this, because we don't provide an evaluation license, because once you've done the inversion, then you would have it complete. So if you are happy with what you've seen, then I'd love to get you started, and then I can always help out with support if you get stuck at any moment thereafter. So thanks for your time, and what do you think?